compute all ordered triples x comma y comma z of real numbers satisfying this system of equations. xy plus z equals 40, xz plus y equals 51, x plus y plus z equals 19. Normally, we would have a system of equations, right? 3 equations with 3 unknowns, and it will have a unique solution. All we need to do is make things cancel, right? The most typical type of system of equations is the linear system, where instead of multiplying variables like x and y together, we just have a bunch of constant multiples of x, y, and z. But in this case, we do have a little complication because of that x, y, and xz, right? One way to think about solving this question is, how can we get rid of those products, or at least make them more manageable? And one way to do that is, well, we can, for example, eliminate x, or we can do something to combine these equations in order for that product, right, to be less scary. One thing we notice is that the y terms here match up and the z terms match up here. So it turns out if we add or subtract these two equations, we can end up with an expression that is nice. In this case, the move is to add these two equations, and you'll see why later. So we get xy plus z plus xz plus y is equal to 40 plus 51, right? And if you rewrite this to group them using, grouping the y's together, xy plus y and xz plus z, we can see that when we add these together, well, we get y times x plus 1 plus z times x plus 1 equals 91. And as a full factorization, we can group those together by the distributive law to get y plus z times x plus 1 equals 91. If we had done the same thing with subtracting, right, that does yield an equation. But notice that when we group them up, yes, we are still able to factor them, right, as always, but notice the terms that we end up with. Y minus z, x minus 1 versus y plus z, x plus 1. I prefer this one because all of the terms are the same sign, right? X, y, and z are both all positive, and that is relevant because if you look at this final expression here, we also have a number for x plus y plus z, right? Notice that means that if we that means that x plus y plus z is equal to 19, and, right, that suggests that we should assign grouped values to these, right? Let's say y plus z equals a, and x plus 1 equals b, so that ab equals 91, and notice that we can simply write a plus b, well, that's just equal to y plus z plus x plus 1, and notice that that's just 19 plus 1, or 20. So now we have a nicer, much nicer system of two equations, right, in a and b, which are real numbers satisfying a sum and a product. We know how to solve these, right, pretty easily by just writing, right, substituting a equals 20 minus b into the upper equation. And let's see what we get. Well, ab equals 91, so then we end up with b, right, a becomes 20 minus b times b is equal to 91. And if we expand that out, we can get a quadratic, which we can solve or factor, right? And in this case, I'm just going to use difference of squares, right? Negative 91 plus 100 to get 9 here. So we get b minus 10 equals plus minus 3. So b is 10 plus minus 3. And that gives us two values, 7 and 13. So remember that we can also solve for a, right? In each of these cases, we get 13 if b is 7, and 7 if b is 13. And now we can just say, let's just substitute back, right? Those x, y, and so on, right? So we get y plus z was a, so we have two possibilities, right? Y plus z is 13, and x plus 1 equals 7, which means x is 6, right? Or y plus z equals 7, and x plus 1 is 13, which means that x is 12. Now, we're almost done, right? We have two possibilities here, but we can't really do anything now unless we know that, remember, those two first equations, which we haven't entirely used, right? We only used their sum, but actually we get more information from the fact that, for example, xy plus z equals 40. So remember that we can use previous equations still. And we get that xy plus z equals 40. Well, we know x equals 6, so 6y plus z equals 40. Y plus z equals 13 from here. So you subtract those and we get 5y is equal to 27. So y equals 27 over 5. And it follows that z must equal 13 minus that. And we get 38 over 5. So one possible triple is then 6, 27 over 5, 38 over 5. We can do a similar strategy on this, right? xy plus z equals 40. That gives us 12y plus z equals 40. Subtract that from y plus z equals 7. You get 11y equals 33. So y equals 3. And then it follows that equals, y plus z equals 7, so it's 7 minus 3 or 4. So the second possible triple is 12, 3, and 4. So we have two possibilities, 6, 27 over 5, 38 over 5, and 12, 3, 4. And those are our only answers.